You ever wonder what's really going on inside a car engine? Or how a giant star keeps from collapsing in on itself? Well, the answer to both lies in this invisible dance that gases are doing all the time, and it's all governed by a set of rules we call thermodynamic processes. Today, we're going to make those rules visible and really get a feel for the physics of change.
So that's the big question, right? How on earth can we predict what's going to happen inside these ridiculously complex systems? I mean, it seems almost impossible. But what's so beautiful about physics is that it takes these huge, complex ideas and boils them down to just a few core principles that honestly anyone can grasp.
And for thermodynamics, it really is that straightforward. To figure out what these systems are going to do, we just need to keep an eye on three key variables and apply two surprisingly simple but incredibly powerful rules. So let's meet our players and learn the rules of the game.
Here they are, our three main players: pressure, volume, and temperature. Now, they're all connected through the ideal gas law, but the real rule book, the one that runs the whole show, is the first law of thermodynamics. The easiest way to think about it is like an energy budget or a bank account for energy. The heat you put into a system, that's Q, it has to go somewhere. It can either increase the system's internal energy, that's delta U, which is basically just the kinetic energy of all those gas molecules bouncing around, or it can be spent on doing work, W, like pushing a piston. Nothing ever gets lost. It's a perfect accounting of every bit of energy. Okay, let's kick things off with our first scenario, an isothermal process. The one and only rule here is super simple. The temperature has to stay constant. Now, think about what that means for our energy budget. If the temperature doesn't change, then the energy of all those bouncing molecules doesn't change either. So delta U is 0. All of a sudden, our budget equation, Q equals delta U plus W, gets incredibly simple. Q equals W. That's it. Every single bit of heat you pump into the system goes directly into doing work. How cool is that?
So how much work are we talking about? This formula here tells us exactly. Now, don't get hung up on the calculus. That integral symbol just means we're adding up all the tiny bits of work as the volume changes. The part that really matters is the final result. You see, the work all depends on the ratio of the final volume to the initial volume. So if the gas expands, V2 is bigger than V1 and the work is positive. The gas did work on its surroundings. If you compress it, well, then the opposite is true. You did work on the gas.
All right, let's switch gears to our next case. Imagine your system is perfectly insulated, like it's inside the world's best thermos. This is what we call an adiabatic process. The main constraint here is that no heat gets in or out, so Q is 0. Now look at our energy budget. It now says 0 equals delta U plus W. Or, put more simply, the change in internal energy is the negative of the work done. This creates this really fascinating trade-off. If the gas expands and does work, it has to pay for that work. And it pays for it by using its own internal energy, which means the gas actually cools down. And if you compress the gas, all the work you're putting in gets converted directly into internal energy, heating it right up.
Now, the math here looks a little different. The rule that governs this process has this exponent, gamma. Don't let that spook you. It's just a number related to the type of gas molecule. The really important thing to see is the formula for work. Notice, it doesn't depend on a constant temperature anymore. Instead, it directly depends on the change in temperature. This shows you the core idea perfectly. In an adiabatic process, work is literally paid for by a change in temperature. So we've got two different ways a gas can expand. One where we keep the temperature nice and steady, and another where we let it cool off as it goes. Now, if you were to plot these on a graph, they might look kind of similar at first glance, but there's a key visual difference that tells the whole story. And here is that story laid out on a pressure-volume graph. The red curve you see is our isothermal process, and the blue one is the adiabatic process. Both of them show that as the volume increases, the pressure drops. That makes perfect sense. But look closely. That blue adiabatic curve is definitely steeper. It drops off way faster. So why is that? Well, the reason is actually pretty simple and really elegant when you think about it. In both cases, as the volume increases, the pressure drops. But for the adiabatic process, you get a double whammy. Not only is the volume getting bigger, but the gas is also getting colder because it's using its own energy to do work. And we all know that a colder gas has lower pressure. So it's that extra pressure drop from the cooling that makes the adiabatic curve so much steeper. Okay, let's look at two much simpler cases now. First up, an isochoric process. Just think of it totally sealed, rigid container, like a pressure cooker before the valve opens. The volume is locked in place. And since the walls can't move, the gas can't do any work. So W is 0, period.
Our energy budget becomes beautifully simple again, Q equals delta U. Every single bit of heat you add goes directly into making those gas molecules zip around faster, raising the internal energy and, you guessed it, the temperature.
So what's our last single constraint? An isobaric process. This is where we hold the pressure constant. For this one, imagine a cylinder with a piston that can move freely but has a constant weight sitting on top of it. Now, if you add heat, that energy is shared. Some of it goes into doing work by pushing that piston up and increasing the volume. The rest of it goes into raising the gas's internal energy and temperature. And the work done? It's simply that constant pressure multiplied by the change in volume, which is exactly that shaded area you see under the line.
So what happens when we start stringing these different processes together? We can create what's called a cyclic process, where the system goes through a whole series of changes but ends up exactly back where it started, completing a loop. And there's a crucial rule here. Internal energy is what physicists call a state variable. All that means is it only cares about the current state, the P, V, and T right now, not the path it took to get there. So if you come all the way back to the starting point, the net change in your internal energy for the whole cycle has to be 0. And if the total change in internal energy over a full cycle is 0, what does our first law tell us? It tells us that the total heat you put in, Q total, must equal the total work you get out, W net. And that, right there, is the fundamental principle behind every single heat engine ever built. It's that simple.
So let's put this all together in one big summary. First, isothermal. Temperature is constant. The key takeaway? All the heat you add becomes work. Next, adiabatic. No heat gets in or out. The work that gets done is paid for by the gas's own internal energy. Isochoric. The volume is constant. No work is possible here, so all the heat just goes into raising the temperature. Isobaric. Pressure is constant. The heat energy gets split between doing work and raising the temperature. And finally, the cyclic process. When you get back to the start, the net heat you've added equals the net work you get out. This is the blueprint for an engine.
So you see, these 5 processes aren't just some abstract physics concepts. They are the literal building blocks of our modern world. By combining them in clever ways, we can design everything from incredibly powerful engines to super efficient refrigerators. So the real question now isn't just about what can we build, but how can we master these rules to build a smarter, more efficient future?